Hello and welcome to your folder. So here's the files that are there so far. They'll keep on coming in. So once you see them, just give me a sec. Once you see them coming in, so you've got 8 complete, 9 complete. Once they start coming in, they'll start landing in your folder. Now you can see, how many do we have? 14. 9 plus 8 is 17, so there's 3 missing, so that's actually not all that many. Oh, hang on a second. Okay, that's not quite true, because these ones are V, R, and I, so these are 3 each. Whereas the other one's just B, so that's 1 each. At any rate, you can see they're coming in, and that there's not as many in here yet as it says there are there. And that is because this, this folder will be a day or two behind because LCO puts the image up as soon as it's available. The OSS pipeline actually waits until the end of the observing night on purpose to collect all the images from the night. There's a story about that you can read in the conference paper. But it does that, and it waits a few extra hours just to make sure that it's all landed back in Santa Barbara and it's all been processed. So it's kind of a safe kind of time to do it. And then it downloads and then processes them, which takes, depends how many images there were, but can take a few hours, and then it uploads it and then downloads. And so there's a period of time, usually a day or two, between it arriving at LCO and you being able to go in and go to data and click and get these files, which you won't be able to open unless I tell you how to, which are named really weird things. They're not really weird things. You can see there is a date there, and that's the camera, but I mean it's non-human readable. There's lots of benefits to the OSS pipeline, but the first one is the file name makes sense. So there's your object name, there's the filter. Ignore these twos, they're placeholders. Exact exposure time. Because you don't want dots in the file name, D is a dot. So here is the date, air mass. Remember I was telling you about air mass. So most of them were taken rough, 45 degrees ish. This is the Julian date of the image and which camera took the image, KB29 or KB88. So you can go to LCO and somewhere around here in planning tools, and you can go down to observatory status. Let me just get that over there. And you can have a look down here. We'd search the page, but there's KB29, so that's in Tenerife. And then KB88, also at Tenerife. So your images have been taken from Tenerife. Or the ones that are there so far anyway. So these are all the cameras, tells you if there's a problem with any of them. But they'll all be coming out of these 0.4 meters. Yes. Couple in Hawaii, couple in Siding Spring. There. So you should be getting more. If you have a look at if we go back, you can see that, keep on going back, that some are not being taken. Probably at periods of times where Siding Spring and Hawaii are in darkness, but for some reason they haven't been taken. Could be rain, could be anything. Okay, but now you've requested all of these images, which is nice. But you don't want to keep on taking images over and over and over if you've got the wrong exposure time. So I'm going to, there is a thing I sent you. It's also in, I'll attach it to the email. Also testing for correct exposure times. So I've sent you this. You have it. It tells you how to do it in Astro Image J. I'm going to do it in Macali because I know that better. But it's the same thing, you just look in a different spot. So it's loading up. Okay, just before I do anything, you see in my computer, I can double click on an image and this thing called Fits Liberator opens up. So that's in the software folder of the OSS materials, works on Mac and PC. That's what I use as my kind of thing that works when I double click, because it's really good. First thing you do is stretch linear, change it to this. It makes more sense. 0.4 meters have this weird background noise stuff going on, but at any rate, yeah, you can zoom in and out and around, scroll over things and see up here stuff. It's just good to see what's happening in the image. I can see just now, if I zoom in, and I just look at the input up here, I can see that not many photons were collected for this star. And I'm assuming this is our exoplanet. You might want to have a look at the star field and then compare it. You know, if you look at my computer down here, I have a ladder here. Well, let's just try. Epic 2059 88562. Assume that's the name. Yes. Okay, so we'll have a look here. Wait for Australia's slow internet to catch up. Okay. I'm not seeing that in the image, really. Now I'm just getting it roughly. Yeah, I'm not seeing the pattern. I know here's the pattern. Dot, 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 dot. Might be dot, 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 dot. So if I look up here, this is curious. Okay, so first thing to do, check the right ascension and declination. Maybe I'm just looking at the wrong star. I've got right ascension 6 here, 6.22. Have a look down here. We do have a WCS, World Coordinate System. So this is stuff that I'm not expecting you to know. Okay, so our area of reference point 336 minus 15. Yeah, so minus 15, yeah. It's roughly on target. What we can do with Aladdin, so you've got Aladdin downloaded now. So we've got here. Let's load the image in. So we can go and open local file. Okay, this is not what I was intending to show you, but because I'm sorry, because I'm confused as to which star's which, we can go into. Oh my god! Remember where everything is. Think it's in here. Yes, should make. Aladdin doesn't have nice shortcuts that I usually have. So I'm going to look at V because it's usually the best behaved filter and open that up. Okay, so that's our image. Oh, smudge. Uh, image. Can I blink? What I'm seeing here, what I'm seeing there doesn't look the same. That's so strange. Maybe you can see it and I can't. Okay. I'm going to try something. We can go and get an image from Deep Sky Survey, which is just a survey of the night sky that it just took the whole entire night sky. We can go and get a 20, well, the camera's about 26 arc minutes. I should have put bigger, but we'll download a black and white image here. So this is the image from the sky survey. This is the image from the camera. Okay. Blink them together. This means that it'll get each image and put them on top of each other, and we should flick back and forth so we can see which image is which. Okay. So maybe I am blind. Okay, and we've got the coordinates here, and we can roll over. Okay, I'm blind. So that was live science. We should, if you write those instructions down, that would be cool. So what was the coordinates of Eric? Oh my god. So I imagine inside your proposal you have the coordinates. Details. Okay, there we go. That's what you asked for. 336233. 233 minus 1604. Okay, so it is that star. So there you go. I taught you something I didn't intend you to do. How to see which star is which in your image and make sure you've got the right one. Okay, so you can see that the sky survey image is square. No. Oh, that's really strange. So our image is not meant to be square. It's meant to be a rectangle. Oh, I see what happened. I see what happened. Okay. Actually don't know how to stop this blinking. But can you see, if we have a look at that, it's rotated. So there's the two stars, and there's the two stars. Right? And I thought, so east is left in one, and north is left, right up in the other. And then I was looking at the other image thinking it was the same, but they're switched north and east. Sneaky coordinates. So it actually, this is our image from the camera. Sorry. And this is the image from the sky survey, which was taken in the 80s or whatever. So sky survey is a square image. Our image is a rectangle. So 0.4 meter does rectangles. And the blinked image is got the rectangle and turned it around. Well, there you go. So anyway, but you can see now this is how you can actually see which star is which. So you've got The rectangle is ours. You can see it doesn't go as deep. You can't see these dimmer stars because our exposure is quite short, but you can see the quality is probably better. I'll tell you why I think that at some other time. But anyway, so the star's in the center of the frame. We're happy with that. Okay, so I ID'd the star. Woo. So the next thing we're looking at is, following these instructions. And you can follow them along. But basically, you can read it, but we want to be in this range. And maybe in the lower end of that range. So there's instructions to use AstroImageJ. You can use that. That's what I'm encouraging people to do. But whoops. But I've been using Macaulay. It's even simpler, but it only works on Windows, and it's not quite as powerful. So But to explore what exposure times you might need, we'll go in here and we'll get the image open. Find our star, which we know is going to be in the center of the frame, so that's not so hard. And it's rotated around. So this is our star here. So let's go and have a look. Okay. So if we scroll over, right, we can see in the count box there will be a similar thing in AstroImageJ. We can actually start to see the individual pixels if we zoom in. So 800, being in the thousands is pretty good, but you can get up to tens of thousands. But what we want to do is measure how many counts from the star just by itself. So an explanation, because you may not have done this with double stars, but it's in the Our Solar Siblings material, but you have not actually done. Little did you know, but I just left the room for about 2 hours. Seems like a seamless transition, the magic of recording. So anyway, continuing on, hopefully I remember where I was up to. So, if we imagine we can draw a slice across the star, which you actually can do in Macaulay, okay? If we look at each of these as an individual pixel in the camera, if we draw a line across, it goes up, and then it goes down, and then that's cool. You see, like, this is the star. It's a bit of an odd shape, it should be smoother. There's a few reasons why that is. But you see, we come back down here, and there's still stuff underneath here. That is because you have the sky. So, what you really want to do is you have this graph. Sorry. We'll have that, and then we'll have this, and then change color, because why not? You've got that profile. Everything in astronomy looks like this curve, incidentally. So here's the light you have from the star, and then you have this other light here. Okay. So when you're looking at this, what you want to do is, I'll just do it very quickly. You draw a circle around it. You count up all the stuff, all the counts, all the light from the star. Yeah. But then you want to, you've got the light from the star and the light from this background stuff. So if you go into OSS, Project 3, PowerPoint 2, Class 2, if we go in here, and I'll pause. Here we have a part of Our Solar Siblings where students would get to the point of learning stuff, so you can use this PowerPoint if you want. I'll go through it quickly. It doesn't do full screen very well on recording. I'll just do it like this. Don't worry about that. Okay, photometry. is photo and light. You can read that. There's an actual CCD, there's a penny or a nickel, whatever you call it. Lots of pixels, it collects light in buckets. What it is, photoelectric effect, photons hit the silicon, generate electrons, they sit in the bucket, and then the bucket's read out. That's a nice animation. White pixels have higher numbers, it's digitized. Dark pixels have lower numbers. So yeah, what we do is we put a circle around the star and then count up all the light within the star. So I made a kind of simple example here. So if we're going to measure this star, and this is kind of the numbers from the pixels, like if we have a look at the image, we can scroll over and you see over here the count changes. Yeah, so it varies. There's a variation just due to the noise. And then we can add them up, and then it's 45 counts if we add them all up. Do I get to something down here? Should actually add this diagram in. Point I'll get here, but basically we're adding up this, which is the star. But you see how there's 1, 2, 1, 2, 1, 2, 1, 1, 2, 2, 1, 1, 1. It's not 0, and that's what we're seeing in our image. And in my diagram, we have this extra light down here, and what we want is to measure just this light here. We don't want that stuff. And that stuff here is so if you look at the image from rural versus city, the rural site, nice contrast, it's the same exposure time, but here the city, you have all this light stuff. So light comes from light pollution from the city, light comes up, hits dust in the atmosphere, comes back down. Also have the moon. So if the moon's over here, it can reflect light into the telescope. You don't actually use these big telescopes to point them at the moon, but you get reflected moonlight. You also have light reflected from dust in the solar system into the telescope, so you can see that if you took the image at different locations, you'd have different sky brightness. You also have the sky glowing itself due to different types of molecules and stuff hanging out. But there's light everywhere, and what we need to do is some type of method to get rid of the sky. We do a different method using that PowerPoint, but this method, you have this circle. Well, it's meant to be a circle, but of course it's a gridded system. And then you put this aperture around it. Well, you put the aperture around the circle, and then you put this annulus, is what the word is. And so you're assuming that the light underneath the star here is sort of similar to this light. And so you take the average per pixel value of light in this annulus and subtract it from each of the pixels of the star. That's the general principle, or something along those lines, but you get the idea. So you have the star here, it has 26,322. That's how many counts there was, but once you take off the sky, there's actually only 22,621. So we can see actually at the moment, just looking at our star here, that in my recommendations here, we want it for 25,000 to about 250,000. So we could, and exposure time it will be a linear thing. If we double the exposure time, we should double the counts. So for this filter, which is the V filter, we could double the exposure time. And if we double the exposure time, the signal to noise is, well, not is, it's not even approximately, but I'm going to say approximately, square root of the number of counts. And so those are counts. And these are counts of how many electrons you captured, which is related to how many light, how many photons were counted, but not exactly. But what we want to do is make sure that this is in a pretty safe range. So if you wanted to have a look at the V filter in your proposal and double the exposure time, so here you got 15 seconds. So I mean, your binary might be in a low ebb, or it might be in a high ebb, as in it might be at the brightest part or it might be at the dimmest part, but you don't know. But at any point, being in this range is okay, because if we double it and it goes up to about 50,000, that's okay. We know that the eclipsing binary is not going to get more than 3 times as bright, so, and 150,000 is still in that safe range. So trying to aim to get just one image that's 50,000, you're never going to get it perfect, but something over, significantly over 25,000 and significantly under 250,000 is good. The reason it's good is it can handle up to 750,000 if something surprising happens, but you want that slack room up there to make sure if, you know, like a supernova goes off, that you capture it. And you also want enough counts, because that signal to noise is a function of the square root of the number of the counts. So if you double the exposure time, that's actually a 1.4 times increase in signal to noise. Yeah, that's about it. Yeah, I guess I can show you this graph. So above 10,000, the noise is about the same, and 1,000,000 is towards where you start overexposing these cameras. So why I'm saying 25,000 to 250,000 is because you're here, you're safely away from where it gets noisy down here, but you're not too high that you're starting to get to the overexposure limit. So getting your star in that range is good. So we just looked at the V1 there. You'll notice that it'll be different in the other filters depending on what type of star it is. We only had one color from Kepler, so we don't even know what kind of star it is, if it's a red or a blue star. So let's go have a look in the I filter. If we go in, now we know this one's the one. So zoom, zoom, zoom. We'll just do that again. Bing! Okay, see now the I filter, we don't have as many counts. So maybe we might like to triple this exposure time. That might be a good idea. And if we go to B, see this is high already, but it may be the case. See, we can't even. Because B is less sensitive, sometimes you can't actually see the other star. You can't really see it in V either. So I'm just going to make sure we've got this arc along here and that one. Okay. Arc along here and then that one. Let's check again. Yes. Okay, so this one. Let's do that. So this is already twice the exposure time of the other filters, but see, the count still isn't twice as long. So even the B might do well with 2 or 3 times exposure time. So set it up to 90 seconds. And we want it to be in that range because we're only just getting one shot every now and then, so we want something that has very good signal to noise. And yeah, that's the general principle. So that's how you test your exposure times. So it might be annoying, but you might have to go through your different filters and see what exposure time would be good to set, and then cancel the proposal you've got and then put another proposal in. It starts collecting higher exposure stuff for the star. So that's in testing for correct exposure time, and you have that class 2 thing there. So let me know if there's any questions. For some reason these always go for half an hour. There's no rhyme or reason for it, but I may as well use the last 5 seconds up by going, awesome, that was great.